This is B. Naresh, working as assistant professor in EC department here. So we are going to discuss subject is electronic devices and circuits. So in that today we are going to discuss the PN junction formation, biasing of PN junction and its characteristics. So before going to this PN junction formation, first we need to review the what are the materials actually. So we know that we're having three types of the metals. One is the semiconductor and insulator. Another one is a conductor. So most of the cases we are going to use a semiconductor metal here. So actually the semiconductor is a media, means interfacing media between. So a semiconductor is a electronic voltage is induced in between insulator and conductor here. And we are having the two types of the semiconductors here. One is intrinsic semiconductor, another one is extrinsic semiconductors here. And a pure semiconductor itself, it is called as the intrinsic semiconductor here. And while adding some impurities to an intrinsic semiconductor is nothing but your extrinsic semiconductor here. So the addition of this impurities to a pure semiconductor is nothing but a doping concept here. So based on these doping levels here, we are forming the two types of the metals here. One is the P-type extrinsic semiconductor, another one is your extrinsic semiconductor here. So first we are going to form the P-type semiconductor here. So if you want to form the P-type semiconductor, we are going to add a trivalent impurities to the P-type semiconductors here. So when we are adding this trivalent impurity to the pure semiconductor, then it is acts as the P-type extrinsic semiconductor here. If you take some examples, and here this trivalent impurities are taken from the third group elements here. Let us take some examples like aluminium, indium, gallium based on this. So these are the materials added to the some intrinsic semiconductor. Then it forms the P-type extrinsic semiconductor here. While forming this a trivalent impurities or a third group elements to the pure semiconductor, it creates a majority of the charge carrier, that is holes here. So means a more number of holes are creates when we are adding this a trivalent impurities to the pure intrinsic semiconductor. And here in this P-type semiconductor, the majority charge carriers are holes here. Similarly, we need to create a N-type semiconductor here. So if you want to create the N-type extrinsic semiconductor, a pentavalent impurities or the fifth group elements are added to a pure semiconductor, then it creates the N-type extrinsic semiconductor. The examples like arsenic, antimony, so these are the some pentavalent impurities group or a fifth group elements, and these are the fifth group elements are added to either a pure semiconductor, then it creates the N-type extrinsic semiconductor. So while making this doping concentration or the pentavalent impurities to the pure intrinsic semiconductor, it creates a more number of charge carriers in the form of electrons here. And here, these more number of charge carriers are electrons. Why? Because of that. So these are the five fifth group element. If you have in the 5 valency electrons in the outside the valency band here. So when we are forming or we are doping this a fifth group elements or a pentavalent impurities, 4 of the valency electrons are paired with the intrinsic semiconductor, and another electron, the fifth electron, is not paired with any another fourth group elements is not formed with any another covalent bond here. And this extra electron acts as a donor here. So that is the reason in N-type semiconductor it contains a more number of donor atoms here. And here the majority charge carriers are your electrons here. So that is the reason if you are adding the trivalent impurities, it creates the P-type extrinsic semiconductor. A pentavalent impurities are adding to the intrinsic semiconductor, it creates the N-type semiconductor here. So from these doping levels, the p-type semiconductor contain a majority charge carriers or holes. In an n-type semiconductor, the majority charge carriers are electrons here. Now by using these two metal, now we are going to form the p-n junction here. So what is the p-n junction? So p-n, the p is means p-type extrinsic semiconductor, where n is the n-type extrinsic semiconductor. So we are taking the two different materials, p-type extrinsic semiconductor as well as n-type extrinsic semiconductor here. So if you want to form this p-n junction, let us take this is your a semiconductor. Let's take the semiconductor material, and one half is doped with p-type, another half is doped with n-type materials here. And we are combining these two metal means this is a plain semiconductor. In that plain semiconductor, one half is doped with a trivalent impurities, then it creates the p-type semiconductor. If you are doping the pentavalent impurities in another half semiconductor, then it creates the n-type extrinsic semiconductor. And this boundary is used to establish the connection between the p-type and your n-type materials here. And this formation of this p and n or interconnection of the p-type and n-type material is nothing but your p-n junction here. So what happens? And just now we observed that while doping some trivalent impurities to the intrinsic semiconductor, the majority charge carriers are holes. And here these are the holes representation here. The majority charge carriers are holes. And hole concentration is a positive charge here. And similarly, when a pentavalent impurities are doping to an intrinsic semiconductor, it creates an n-type extrinsic semiconductor. And we know that based on the doping level concentration, and the more number of electrons are created here, and hence the electrons are represented this dot notation here. And here, in this n-type semiconductor, so here these are the majority charge carriers, and here the majority charge carriers are electrons. And in the p-type, the majority charge carriers are holes, and it also contains some of the minority charge carriers in a p-type, that is electron. In n-type also it contains some minority charge carriers. The minority charge carriers are holes here. So in a p-type, the majority charge carriers are holes and the minority charge carriers are electrons. Similarly, in n-type semiconductor, the majority charge carriers are electrons and the minority charge carriers are holes. When we are forming this p and n junction, due to its kinetic energy, and the movement of the charge carriers or the charge carriers are diffusing from the one region to the another region. Diffusing the one region to the another region. So in this case, if you are taking the n side, the majority charge carriers are electron, and due to this kinetic energy, the electrons are diffusing towards the another side, that is nothing but towards the p side here. So here, what are the majority charge carrier? This is the electrons. These electrons are diffusing towards your p side. Similarly, the holes are diffusing towards your n side here. Electrons are diffusing towards the p side and the holes are diffusing towards your n side. Due to these diffusions or the movement of the charge carriers and how much distance it travels here. So based on the energy of the electron or a hole, due to that kinetic energy, either electron or a hole are diffusing from the one region to the another region here. So based on this principle, electrons are diffusing from the n region to the p region, and the holes are diffusing from the p region to the n region. And suppose if energy is if any charge carrier it loses its energy, then it becomes a immobile ions here at nearby this area. So whenever this let us take another, if I'm taking like this is the p-type semiconductor, and this is the p-type, and this is the n-type semiconductor, and here this is the electrons are majority charge carriers here, and here the holes are the majority charge carriers here. Let us assume that, and we know that this electron is the negative charge particle, and due to this kinetic energy, this electron is diffusing from the N region to the P region, and based on the energy of these electrons, and is traveling from this place to another place or opposite direction here. So while it's traveling, due to this energy, whenever it loses that energy, it becomes the immobile ion. Means this negative charge particular becomes immobile. That becomes the positive ions. So that is the reason a positive ions are established nearby the N-side junction. Similarly, whenever the holes are diffusing from the P-type material to the N-type material, and based on its kinetic energy, while this hole diffusing from this P region to the energy N side, if that charge carrier it loses its energy, it becomes an immobile ion, and that immobile ion becomes the negative charge particular here. So that is the reason, and under due to this internal energy, the movement of the charge carriers from the one region to the another region, it means the electrons are diffusing from the N region to the P region. Whenever it loses its energy, that electron becomes the immobile ion, and that is represented as your positive ion. That ion is established nearby the junction. Similarly, whenever the holes are diffusing from the P region to the N region, when it loses its energy of that particular hole, it becomes the immobile ion, and that ion is represented by the negative ion. So due to this, a voltage means a electronic induced voltage is generated between the P type and the N type material. And this region here it is called as the space charge region. This region is called as the space charge region, or it is also called as some electronic induced voltage or a barrier potential. It is also called as a barrier potential. So this barrier potential is developed by the movement of the charge carriers from the one region to the another region. So whenever the charge carriers are moving from the one region to another region, whenever it loses this energy, it creates the immobile ions, or it establishes the immobile ions nearby the junction, and that immobile ions creates the barrier potential. So that is the reason the movement of this charge carriers from the N side to P side, or the holes are moving from the P side to N side, a voltage is established between the junction. So means whenever the electron becomes immobile ion, that is represented by the positive ion, and whenever the hole becomes immobile ion, that is represented by the negative ion, and that gives the potential barrier of your PN junction here. So here I explained the same concept here. So in this case, let's take this is a representation, and this is the semiconductor, and this notation is holes here. This representation is holes, and here this representation is electrons here. So in N type, the majority charge carriers are electron. That is the reason more number of electrons are available in your N type semiconductor. Similarly, if you consider the P-type semiconductor, the majority charge carriers are your holes here. So that is the reason it contains more number of holes, as well as this P-type material is also contain the minority charge carrier is the electrons, and this is electron representation. Similarly, if you come into your N-type semiconductor, the majority charge carriers are electrons, and the minority charge carriers are your holes here. So due to this kinetic energy, this electron property is diffusing from this N region to the P region, and similarly this electron is diffusing from the N type to P type material. Similarly, this hole is diffusing from the P type to your N type here. While traveling from one region to the another region, whenever it loses this energy of charge particular, it becomes the immobile ion. So whenever the electron loses the energy, it becomes immobile, and that is represented by the positive ion. This is the notation for the positive ions. And similarly, whenever the holes are diffusing from the P type to N type, and whenever it loses its energy, it becomes an immobile ion. It is represented by the negative ion. And this region, and this negative ions and the positive ions are established by nearby the junction. This is nothing but the junction. the P type and N type are combined at one point. That is nothing but a PN junction. So these immobile ions are established at the nearby the junction. This region is called as your space charge region or a potential barrier region here. Now coming to you, then we're going to observe what is biasing here and how to identify the characteristics of this PN junction here. So up to this point, we observed that what is the P-type material and what is the N-type material, then how we can form the PN junction here. Now, if you want to make the conductivity in a PN junction, then we need to apply some external force. Why? Because of that, we need to further the movement of the charge carriers from the one region to the another region. We need to apply some external force. So that is the reason. For this PN junction, we made the two types of the electrodes. One electrode is made with the P type and another electrode is connected with the N side. So for this case, let us take this is your PN type and this is PN, P and N. So one electrode is created at the P side. This is called as a positive electrode. And one electrode is established across the N side. This is represented by the negative electrode here. And for these two terminals, we are going to apply some external force, the further movement of the charge carriers from the one region to the another region to generate the conduction across the PN junction here. So the way of approaching this external force to an PN junction is nothing but your biasing. The way of applying the external force or the way of approaching the external force to an PN junction is nothing but your biasing. So what is the need of this biasing means to make the conductivity in a PN junction, we need some biasing concept. Means we need to apply some external force, either the P side or N side, the further movement of the charge carriers to conduct the flow of charge in a PN junction here. So based on this biasing, we are on the three types of the biasing concepts here. One is your zero bias, another one is forward bias, and the third one is reverse bias. So coming to your first case, in zero bias means there is no external force. There is no external force between the P side and the N side, and that type of the biasing concept is called as your zero bias. And coming to your forward bias, what is the meaning of the forward bias? And the P side, we made one electrode. That electrode is represented as your positive electrode. And for an N side, we made one electrode. That electrode is represented as your negative. And this is nothing but this negative is also represented as your cathode. And the positive side, this electrode is represented as your anode. Means, so externally we need to apply some force. For that force, we are taking in terms of your voltage source. Means, a positive voltage source is connected to positive terminal of this PN junction, and a negative voltage source is connected to N type of this material or cathode of PN junction, and that type of the biasing is called as a forward bias here. So the positive source of the battery is connected to positive terminal or anode terminal of the PN junction, or the negative source of the battery is connected to cathode of PN junction, and that type of the biasing is called as your forward biasing here. Similarly, the another biasing is your reverse bias here. So means, what is the reverse bias here? Again, let us take this is the PN junction. This is the P side and N side. P side we are having this anode, and the N side we are having the cathode. So means, we are going to apply this for anode side, we are applying the negative source of the battery, and for the cathode source, we are applying the positive terminal of the battery. Means, the negative source of the battery is connected to anode of the PN junction, and the positive terminal of the source is connected to cathode of the PN junction. This type of the biasing is called as reverse biasing of PN junction here. So that is the reason we are on the three biasing concepts here. One is a zero bias, another one is a forward bias, and another one is your reverse bias here. We will see what happens under the zero bias, under the forward bias, as well as your reverse bias here. So coming to the first one, that is nothing but a zero bias, and it is also called as unbiased diode here. Zero bias, it is nothing but unbiased diode. So why it is called as unbiased diode means we are not applying the any external force to an PN junction. That is the reason it is called as a unbiased diode. Now we'll see what happens if you're not applying any external force to an PN junction. What happens due to that internal conductivity here. So for this case, let us consider a semiconductor. In that semiconductor, another one half is doped with a P-type material, another half is doped with your N-type material. And we know that so based on the doping concentration, based on the trivalent impurities, means here in a P-type, so we are taking the third group elements, and these third group elements are added to the or doping to the a pure semiconductor. Then it becomes your a P-type extrinsic semiconductor. But to form this N-type semiconductor, a fifth group elements are added to this intrinsic semiconductor. Then becomes the N-type extrinsic semiconductor. So already we observed that based on the doping concentration, the P-type semiconductor contain the majority charge carriers are your holes. The majority charge carriers are holes, and the minority charge, these are the minority charge carrier. The minority charge carrier is the electron. And similarly, the N-type material, so due to the doping levels, means pentavalent impurities are added to this intrinsic semiconductor. Then becomes your N-type extrinsic semiconductor here. And due to this doping concentration, the majority charge carriers your electrons and the minority charge carriers are your holes here. And due to this unbiased means, and this is electrode, and this electrode here it is represented as anode, and here this electrode is represented as your cathode here. So in between this anode and the cathode, we are not applying any external force. Hence, this type of the biasing is called as your unbiased or zero biased here. But what happens in this under unbiased condition? So what happens here due to this internal energy of charge particles? So what are the charge particles here? Here holes as well as the electrons of the charge particles here. Due to this kinetic energy, the electrons are diffusing from these are the electrons. The electrons are diffusing from the N side to the P side. Similarly, the holes from the P side to your are diffusing towards your N side here. While doing this kind of operation, while doing this under condition, so what happens here? Due to this energy of either electron or a hole, it diffuses the charge carriers from the one region to the another region, means traveling from the one place to the another place. Whenever it loses its energy, and the charge particular becomes the immobile ions, means so it becomes the standby position. It does not move in the further until under further space here. So that is the reason, and it becomes the one immobile ions, and it changes the polarity of that ion. So here the electron is a negative charge particular, hence it becomes the positive ion. Similarly, whenever the holes are diffusing from the P side to your N side, whenever it loses its energy, it becomes an immobile ion, and that is represented by negative ion. So under this unbiased condition, it creates the one depletion region, or that is not that region is called this region is called as the depletion region, or it is also called as your space charge region here. And this space charge region is also nothing but a potential barrier. Here it is represented as a V gamma here. So means if you want to make this conduction, we need to apply, means we need to break this potential barrier. Then the further movement of the charge carriers from the one region to another region to generate the flow of conduction across this PN junction here. So under this unbiased condition, so from this observation, we observed that under this zero bias or under this unbiased condition, it establishes a potential barrier between the P side and N type material. Or a junction itself, it contains a potential barrier or a space charge region. So based on the either forward bias or a reverse bias, either we need to reduce that potential barrier space width or increase to further to generate the flow of conduction in a PN junction here. We'll see what happens under what forward bias as well as your reverse bias here. But If you want to generate some flow of conduction under this PN junction, your applied energy should be greater than of this a potential barrier voltage here. Then only the movement of the charge carriers are diffusing from this region to the another region to form the conduction in PN junction here. Now coming to your forward bias. So what is actually forward bias? So in this case, again I consider this PN junction, or otherwise let us consider a semiconductor. One half is doped with the P-type material, another half is doped with the N-type material. And here this is represented as anode, and here it is represented as your cathode. So what is the meaning of forward bias here? So biasing means we need to apply some external force to an PN junction, the further movement of the charge carriers from the one region to the another region here. So here, to make this forward bias, let us take, we need to take some external source. That external source I consider as the voltage source here. And this voltage source contains the two polarities, positive polarity as well as a negative polarity. The positive polarity of the source is connected to anode of a PN junction, and similarly the negative polarity of the source is connected to cathode here. So what happens here? So this type of approaching is nothing but your forward biasing concept here. Whenever the anode is connected to positive pole of the battery and a cathode of PN junction is connected to negative pole of the battery, then it becomes the forward bias. Now we'll see what happens here from this unbiased diode to forward bias. So let us take, just you observe this unbiased diode. So in this unbiased diode, we observe this space charge region. Let us take what happens here. This space charge region contains some width here. So this width contains a immobile ions. Those are represented as the negative ions as well as your positive ions. Then coming to here, what happens if you observe this unbiased to your forward biased diode, the space charge region is a decreased. Why it is a decreased means, and here let us take what are the majority charge carriers. Here the P-type is a majority charge carrier, that is the holes are the majority charge carriers, and this hole contains positive charge particle. Similarly, coming to your N side, the majority charge carriers are electrons, and electron is a negative charge particle. So for these majority charge carriers, for the P side, we are applying the positive energy. Means again positive energy and this positive energy. What happens here? Repelling is occurred here. Due to the applying of the same force, repelling is occurred towards the opposite side. Similarly, and coming to your N side, the majority charge carriers are electrons, and electron is the charge particle is a negative charge particle. And for this negative charge particle, we are applying the negative subbiasing source or negative energy. Due to this negative energy, again, this electron is repelling towards the opposite side. Means that we are applying some amount of the force to movement the charge carriers from the one region to the another region here. And due to this approaching of the forward bias diode, due to this approaching of this forward bias energy, the charge carriers from the P side. What are the charge carriers from the P side? The majority charge carriers. So holes are diffusing. So more number of charge carriers are diffusing from the P region to the N, right? So here what happens previously, if you consider this unbiased diode, due to this an external force, this ion is also becomes now energized here. So that is the reason. And this now this if it is energized, this is also again having some property to move further diffusing towards the opposite direction here. So that is the reason. Due to this applied external biasing energy, the movement of the charge carriers from the P side to N side as well as the N side to P side. So hence, what happens here? It decreases the space charge region. Why? Because of that, it breaks this covalent bond structure. It breaks this potential barrier here. Then further movement means to cross the region from the P region to the another region, we need to break this potential barrier. So that is the reason. How we are going to break this potential barrier here? By applying this energy, we are breaking this potential barrier or depletion space charge region. Then what happens here? The more number of the charge carriers are freely moving from the one region to the another region here. So let us take, this is the insulating media. Let us take, if you observe some if you want to allow the conduction from the one region to another region, then we need to make entire the region is a conductivity. So here, what happens here? We are reducing this. This is acts as a normally under unbiased diode. It is acts as a insulating media between the P type and your N type here. But here, due to this applied external force, what happens here? We are reducing this potential barrier space and further movement of the charge carriers from the P side to N side as well as your N side to your P side here. And due to this applied external force, the more number of charge carriers are repelling towards from the P region to the N side as well as the N region to the P side here. Hence, it reduces the space charge region between this P and N type junction. That is the reason I drawn here. The space charge region is reduces. But here, how much voltage is required to reduce or to conduct the flow of conduction? Means we need to break this covalent, we need to break this structure, or we need to break this insulating media. That is represented as a V gamma here. So here we are on the two types of the materials here. One is either silicon or a germanium. So if you are consider the silicon, the cut-in voltage, this V gamma is represented as a cut-in voltage or a breakdown voltage here. So here, if for this case, the silicon, if you are considering the silicon, the cut-in voltage is 0.7 volts. If you are considering the germanium, the cut-in voltage, the V gamma is 0.3 volts. Means whenever your applied input voltage just crosses the V gamma, let us take here I represented as your potential barrier V gamma, and let us this is the Vs. Whenever this Vs is greater than of your V gamma, then what happens here? This space charge region becomes reduces. Hence, the more number of charge carriers are repelling from the one region to the another region. Means what happens here? Electron and hole pair is created here. So whenever the electron and hole pair is created, the conduction takes place across this junction here. So hence, under this forward bias, the more amount of the conduction takes place due to the effect of the which charge carriers your majority charge carriers here. Why? Because of that, the majority charge carriers are repelling from the or diffusing from the one region to the another region. That is the P type to N side or N side to P side. If you consider the P side, the holes are diffusing from the P region to the N region. If you consider the N side, the majority charge carrier, that is electrons are diffusing from the N region to the P region. And due to this applied external force, the more number of charge carriers, electrons are diffusing from the N side to P side to break this potential barrier to allow the conduction across this PN junction here. And for this case, the required input voltage is your applied input voltage should be greater than of your cut-in voltage. The cut-in voltage based on the materials, if you consider the silicon, the cut-in voltage is 0.7 volts. If it is the germanium, the cut-in voltage is 0.3. So whenever this input voltage is greater than of this cut-in voltage, the more number of charge carriers are diffusing from the N side to P side as well as the P side to N side. Hence, the maximum conduction takes place. Under this type, the conduction is takes place from the across the majority charge carriers, and that conduction is represented as a forward bias current, that is represented as IF here. So here it is represented as IF is nothing but your forward biased current here. And similarly, we need to observe the voltage across this PN junction under this forward bias, that is nothing but your forward biased voltage is your VF here. So these are some points how we are going to make this forward bias as well as then coming to your reverse bias diode here. So what is the reverse bias diode? So first, what is the meaning of the biasing here? So biasing means we need to approach some external voltage or external source is connected across the PN junction. That is nothing but your bias. If you want to make the reverse bias, so the negative terminal of the battery is connected to anode of the PN junction as well as the positive terminal of the battery is connected to cathode of the PN junction. Then it is acts as a reverse bias diode. So let us take again you consider the PN junction. let us take unbiased diode. So if you consider the unbiased diode, what is unbiased diode? We observe this one, and this is the unbiased diode. So for this unbiased diode, now we are going to approach the reverse biased diode here. So what happens due to an approaching of this reverse biasing voltage across this PN junction? If you observe this unbiased diode and the reverse biased characteristic, the configuration, the space charge region, or depletion width region is increases. I'll explain why this depletion width region is increases compared with your unbiased diode. So here let's take, this is your anode, and here this is cathode. So your anode is connected to negative pole of the battery and the cathode is connected to positive pole of the battery. This type of approaching is called as the reverse biasing, or this type of the biasing is nothing but your reverse biasing. We'll see what happens due to this reverse bias. And here if you observe the P type, what are the majority charge carriers? The majority charge carriers are holes here. The majority charge carriers are holes. In the N side, the majority charge carriers are your electrons. And coming to the P side, what are the charge carriers here? The holes are your positive charge carriers, and electrons are your negative charge carriers. Due to this applied biasing, and here this majority charge carriers are attracting towards the negative pole of the battery. Why? Because we are applying the opposite energy. Due to this opposite energy, these positive charge particulars are attracting towards the battery. Similarly, and coming to your N side, what is the N side here? The N side contain the majority charge carriers are your electrons, and electron having the negative charge particular. But for this negative charge particulars, we are applying the positive energy. Due to this opposite energy, these electrons are again attracting towards the opposite energy. So that is the reason. So due to this biasing condition, the majority charge carriers do not diffusing from the one region to the another region, but it diffusing towards the battery. So that is the reason. The holes are diffusing towards the negative pole of the battery, and electrons are diffusing towards the positive pole of the battery. Hence, it creates a more amount of immobile ions. Why? Because of that is not paired with any electron and hole combination. So whenever the electron and hole combination takes place, then only the conduction takes place. So, but here, due to this approaching of for reverse bias, the more amount of the charge carriers are diffusing towards only the battery. Hence, it increases the depletion width. Hence, there is no flow of conduction across the PN junction here. So that is the reason. There is no current flows across this reverse bias, but only the small current is the flows due to the effect of minority charge carriers here. So what are the minority charge carriers here? The P type contain the minority charge carriers are electrons. In N type, the minority charge carriers are your holes. But it contains a very less number of the charge carriers. Due to this reverse bias, the minority charge carriers are diffusing from the P side to N side as well as your N side to your P side. Hence, it allows only a minority charge current that is very, very small here. So hence, there is no majority charge carriers conduction across this PN junction under this reverse bias. That is the reason there is no conduction takes place under the reverse biased PN junction diode. So from these three observations, from these three biasing concepts here, so we observe the three biased concepts here. One is the unbiased condition or a zero biased condition, forward biased condition, as well as a reverse biased condition. From these three biased conditions, now we are going to observe the characteristics of this PN junction here. So this is the characteristics of the PN junction diode. We are in the two types of the characteristics here. One is the forward biased characteristics, another one is the reverse biased characteristics. The forward bias characteristics drawn between forward bias voltage versus forward bias current. So hence, here I taken this forward bias voltage is represented as a VF, and this is the forward bias current, and here it is represented as IF. Similarly, under the reverse bias, we observe some characteristic that is nothing but a reverse bias characteristics, and that reverse bias characteristics drawn between the reverse voltage VR and it versus your reverse current that is your IR. And let us take how we are generating the flow of conduction here. If you observe the forward bias condition, so let us take this is the forward bias. Under this forward bias, what happens here? Due to this approaching of this forward bias operation, the majority charge carriers or more number of the majority charge carriers are diffusing from the N side to P side or the P side to N side, then creates the electrons and the hole pairs. Then a maximum conduction takes place under this forward bias whenever your applied voltage just crosses the potential barrier voltage or a current voltage. So that is the reason in this I represented you. So here this is nothing but a cutting voltage or a V gamma. So V gamma is either 0.7 or a 0.3, 0.74 for silicon diode, 0.3 for germanium diode. If you are considered the silicon PN junction diode, the cutting voltage is a 0.7 volts. If you are considered the germanium PN junction diode, the cutting voltage is 0.3. And we observe from the forward bias operation. What happens under the forward bias operation here? Due to that approaching, it reduces the potential barrier region between the P and N side junctions. Hence, the more number of the charge carriers are diffusing from the one region to the other region, and the maximum current takes place across the PN junction here. So whenever this applied input voltage just crosses the current voltage, your conduction rate is increases here. That is the reason I drawn like this here. But under the reverse bias, what happens here due to this reverse bias? The way of approaching this battery to and this PN junction. Why? Because of that, this negative pole of the battery is connected to anode of the PN junction, and the positive pole of the battery is connected to cathode of this PN junction. What happens here? The majority charge carriers of P side and N side are attracting towards only the batteries, not towards the semiconductor or internal semiconductor here. That is the reason a more number of immobile ions are established nearby the junction. Hence, the depletion width is increases. If the depletion width is increases, what happens here? There is no movement of the charge carriers from the P side to N side or N side to P side. Hence, there is no flow of conduction takes place across the PN junction. Hence, there is no majority current, and that is the reason if the applied voltage is increases, what happens here? It allows only the minimum amount of the current. That is the reason I drawn like this here. But ideally, that is a zero. Practically, it contains some amount of the flow of current due to the effect of minority charge carriers. But what happens? If it goes on increasing, so if it goes on increasing this reverse bias voltage, what happens here? It creates a more number of immobile ions across the P side region, across the N side region here. So what happens here? So if it goes on increasing the reverse bias voltage for an PN junction, more number of immobile ions are established nearby the PN junction. So means it breaks down the PN junction, or it breaks down the some diode. Means at certain voltage, means at certain voltage it breaks down your PN junction. That is the reason. What happens here? The diode will be breakdown condition. That mechanism is called as the breakdown voltage. So at this breakdown voltage, the diode is a breakdown, and it allows some amount of conduction here. So from this forward bias and the reverse bias, we observe the two types of the characteristics. One is forward bias characteristics, another one is your reverse bias characteristics here. So up to this point, today we observed that what are the P-type materials and what are the N-type materials, how we are forming the PN junction, and what is the biasing of this PN junction and characteristics of PN junction. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.